Bing, bang, boom. You know what that was? That was the sound of the abominable snowman walking in Waterford, Wisconsin. And guess what happened? It caused this giant earthquake-like thing. Well, you know what earthquakes are measured in? You might have heard the word magnitude before. There's a magnitude of an earthquake. Basically, that's the size of the earthquake, how big or how small it was. So if you've ever heard that word before, it might have been used in that instance, or maybe a different one. But what we're talking about in this section, chapter 4, section 7, is magnitude. So this whole second chapter, part of this chapter, is about scientific notation, magnitude, things like that. And they're all applying different things with exponents. So our 2 learning targets for today. Number 1 is to know that positive powers of 10 are very large numbers and negative powers of 10 are very small numbers. And that'll be the case for any, like, powers of any number. We've learned that when you have a negative number, it becomes a fraction, so it is going to be a very small number then. But also our second learning target here is to know that the exponent of an expression provides information about how big it is, what the magnitude of it is. So we're looking at size of numbers, kind of looking at size of numbers with powers of 10 today. So, a couple things to start talking about. Exponential notation, so everything that we've been doing with exponents so far, is indispensable, meaning it's super important to know because it's used to clearly display the magnitude of a measurement. Now, I might even add here, indispensable in science. You guys have probably used exponents somewhere in science. It really is used a lot in science and math, obviously, but magnitude, the size of things. So magnitude does refer to how big or how small a number is, as we kind of said with the earthquake. Understanding magnitude or size comes down to understanding integer powers of 10, and that's what we're going to mainly work on today. All right, 2 things, and these I think are in your notes. 2 things that are important to know for today. 1, fact number 1, the number 10 to the n power for arbitrarily large positive integers n, meaning it could be anything large there for the exponent of 10, is a big number in the sense that a given number m, if you have a given number m, any number, there is a power of 10 that is larger than it. Okay? And we'll get to explaining that. Fact number 2, the number 10 to the negative n power for an arbitrarily large positive integer. So when you make n bigger, it's actually making the thing smaller. So it's a negative exponent. Is a small number in the sense that given a positive number s, there is always a negative power of 10 that's smaller than it. So let's start working on that a little bit. Here's example 1. Let's look at the world population. Now this is in 2013, so it's a little old, but they don't do a census every year. So let M be the world population as of March 23rd, 2013. Approximately M is 7,073,981,183. So that's approximately the world population. A little over 7 billion. Now we want to find the smallest power of 10 that exceeds the world's population. So what I mean by that is you could take 10 to any power, let's say 10 to the 5th power. We want to see what's the smallest one where 10 is the base, so that it's bigger than that world population. So let's just think about what 10 to the 5th power means. 10 to the 5th power means 10 times 10 times 10 times 10 times 10. Or the shortcut you may know is you just put a 1, and since it's 5 tens, there's going to be 5 zeros after it. 1, 2, 3, 4, 5. And let's put the comma in every 3, moving from the right. So that's actually only 100,000. So we want it to be bigger than that. So let's find one that's just bigger than our world population. Well, if you look at the world population, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. So why don't we try 10 to the 10th power? So that would be a 1 with 10 zeros. I'm going to put our comma every 3. So I've got 10 billion. So 10 billion is larger than approximately 7 billion. And if we were to do one less, 10 to the 9th power, we would only be at 1 million, which is not above it. So 10 to the 10th power, the size of that number, based on the digits we used that as a shortcut, is larger. It's the smallest power of 10 that's larger than the world population. So it has 10 digits and is therefore smaller than any whole number with 11 digits, such as 10 billion. Now 10 billion does have 11 digits, but that last digit is the 1. So it's the smallest 11-digit number. Whereas if you had 99 billion, or 9,999,999,999, that would be the largest 10-digit number. But we're looking at powers of 10. So do you agree with that so far? I hope so. So what we can say from that is that 10 billion is 10 to the 10th power, and that is greater than m, which is our population. So that's the smallest power of 10 that's greater than m. Let's look at another example. Similar. I don't know if you've ever looked at this before, but the national debt is huge. As of January 9th, 2019, it's approximately 21 million, and I'm going to put dollars here, but 21 billion 927 million 500, oh, that's 21, pause here for a second. Sorry, there we go. It's 21,927,536,886,684. That's a really big debt. If we're in the 21 trillion, almost 22 trillion, that's pretty ridiculous. But if you look at that number, let's try to get a sense of how big that number really is, and let's talk about powers of 10. So we want to find the smallest power of 10 that's bigger than that. We could even find the largest power of 10 that's smaller than that, but we're trying to look at powers of 10 that are around that. So let's do what we did with the last one. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 digits in that. So let's look at some different numbers here. Our debt, and I gotta add the numbers to this here, is 21 trillion something something something. So I just wrote out some numbers here. So if we were to take a number that has the same amount of digits and all nines, it would be 99 trillion 999 million 999,999,999. Now that is definitely bigger than it, but that's not a power of 10. That's not something that's easy to work with. So let's work with a power of 10 that would be bigger than that. So if you add $1 to that, you would be at 100 trillion, which is 10 to the 14th power. Now, if we looked at 10 trillion is actually smaller than all of those. 10 trillion is just one power smaller, and it's actually, what, $990 trillion smaller. So let's look at, if there's 14 digits, the smallest power of 10 that is larger would be 14 zeros, which would be 10 to the 14th power, which is actually 100 trillion. And that's quite a bit bigger than what our actual national debt is, but that's the smallest power of 10 that would be larger than it. All right, do you agree with that? But it's also good to know and see that 10 to the 13th power is just on the other side of it. It's actually closer to it, but it's under it. So those are the two that are on either side of it, either side of our national debt, looking at powers of 10. So I want you to take a second here and try exercises 1 and 2 on your own. So pause it here. All right, to go over those two, in exercise 1, we had 15 digits there, 15 digits to work with. So why not try 10 to the 15th power? And if you do that, that is, we have millions, trillions, quadrillions, think it's a quintillion, 1 quintillion, whereas we had 993 quadrillion. And the next highest one that's a power of 10 would just be adding a 1 to it and all zeros. That would be 10 to the 15th power. Now in example 2, it's the same idea. There's just a fraction involved. You can have fractions, but there's still only 5 digits. And it's not going to exceed that with a fraction. So if there's 5 digits, let's try 10 to the 5th power, which is actually 100,000. And 100,000 would be the next power of 10 that's bigger than 78,000. Because if you tried it one less, you'd have 10,000, which equals 10 to the 4th power. And that's too small. We want to go just higher. But it's good to help us estimate and actually see how big these numbers are. So let's move on. Let's talk about example 3 here. Example 3, we prove that we prove what we have observed for all numbers. We've done it with just whole numbers. We want to do it with fractions as well. So we have 2 things to consider here. One is when the number m is a whole number, like in exercise 1 and 2, you just complete it. Okay? You can do that. Whereas in example 2, there was actually a fraction. It's not a whole number. It didn't do much differently, but it's good to understand where it's located in respect to like a number line. So let's look at case 3, example 3. Example 3, it says let m be a positive integer with m digits. So it doesn't matter how many digits there are. If you had a number, for instance, like 999, that is the biggest 3-digit number you can have. I hope you agree with that. If you go one bigger than it, using the same number of digits only as zeros, just put a 1 and then we have 3 zeros, one bigger than it would be 1,000. And there's no numbers, like 10 to the power of 3 would be 1,000. There's no numbers with 3 digits that would be bigger than 1,000. There's only one number there's no numbers that would be bigger, whole numbers that would be greater than, or there's only one that would be equal to it, 999. But any number you're dealing with that's a 3-digit number would be smaller than those 2 numbers. So 1,000 is our power of 10 that we're working with. So if you have 3 digits, kind of like what we've been working with, if you do 10 to the power of 3, so 3 digits, 10 to the power of 3 will always be larger. You can try that for any sample of numbers. Let's use green here. If you had a 7-digit number, for instance, 2,684,200. 7 digits. If you do 10 to the 7th power, it's always going to be bigger. Because it's 10 zeros and a 1, so it's going to be the smallest 8-digit number. Now, example 3, looking at a non-integer or a non-whole number, there could be a fraction. The same idea goes here. This is a little bit confusing, this point right here to look at, but let's just look at the number line. For any number that you're dealing with, 5.5, okay, it's not a whole number. There's always a number on either side of it. So 5 and then one bigger than that, n plus 1 would be 6. Now if you did 10 to the 5th power, or lowercase n, there's only one digit. Let's do 10 to the 1st power, because we're dealing with 1-digit numbers. It will always be bigger. It's just 10. 10 is always bigger than 5 or 6. We could change that up. Let's say we have our number 16 2/3. Well, on either side of that would be 16 or 17. But now they're 2-digit numbers. So 10 to the 2nd power is always going to be bigger. So just picturing it on a number line. The number of digits, if you take 10 to that power, will always be bigger. So that's 100. It's always bigger. Okay? That's the idea that we're working with today, size of numbers. So what's the point in all this? Well, powers of 10 give us a sense of number size, or magnitude, which is our keyword for today, magnitude. Consider which is bigger, 34 to the 7th power or 10 to the 11th power. Which one do you think is bigger? Well, we know 10 to the 11th power would be 1 with 11 zeros. I might have put the commas in the wrong place. So it's 100 trillion. We don't know what 34 to the 7th power is, okay, without actually using a calculator. So powers of 10 are easy to work with, and believe it or not, 10 to the 11th power, even though 34 is a much bigger number than 10, 10 to the 11th power is actually bigger. So it helps to understand powers of 10. And that's our lesson for today. So what I'd like you to do is go ahead and practice with examples 3 through 5, 3 through 6, I think, are on your thing. Read those through and answer those to the best of your ability. And we're going to come back and we're going to practice that next time. That's all for today. Again, our goals for today were to know that positive numbers of 10 are very large numbers. The same thing works for negative powers of 10, are very small numbers, and that's what we're going to touch on as well. To know that the exponent of an expression provides information about its size. All right, if you want to know how to do numbers, examples 3, 4, and 5, and 6, we'll do number 3 together. Actually, we're going to just do number 4 together because number 4 has to do with the negative. So it's, scratch that, number 5 we're going to do together. So the chance of winning a big lottery prize is about 10 to the negative 8th power, which means the chance of getting struck by lightning in the United States is about 0.000001. So which do you think has a greater chance of experiencing winning the lottery or getting struck by lightning? Well, what is 10 to the 0 or to the negative 8th power? If you figure that out, we've done that before. It's 1 over 10 to the 8th power to make it a positive. So it's 1 over 10 to the 8th power would be 8 zeros. That's 100 million. 1 over 100 million. So let's put it into a decimal. And well, actually, let's look at this one. So that's our chance of winning the lottery. And our chance of being struck by lightning, well, that's in the tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions. It's 1 over 1 million. So you have a better chance, significantly better chance of getting struck by lightning than winning the lottery. There's an example with a negative exponent and how you can use those numbers to compare size. All right, that's the last example I want to touch on. Have a wonderful day.